Well friends, let us continue with our discussion on modeling of physical systems. If you recall, during the last lecture we had considered the models of mechanical systems, the translational as well as rotational. Basic equations of the mechanical systems were given to you. The analog with the electrical circuits was also presented with the comment that for mechanical systems, maybe considering the analog, it may be convenient for us to write the differential equations. I think before I go to the thermal and other systems, it will be worthwhile considering a couple of examples. My first example is that of one-wheeled model of an automobile. You will see that how the physical behavior, the physical attributes of a system are modeled into a mass spring damper system. Consider this one-wheeled model in which I consider this m1 as the mass of the vehicle. K1 is the model of the springs of the vehicle, and let me take B as the model for the dampers. Consider another mass m2, this is the mass of the wheels, and I will consider one more spring over here representing the elastance of the tires. Okay? So, you see that this becomes the one-wheeled model of an automobile. Under consideration is the study of effect of the road surface variations. You see that it means I am interested in the study of vertical motion of the vehicle. The vertical motion of the vehicle will come as and when the bumps come on the road or there are other disturbances, the roughness and other things. So, it means as far as this attribute of study of the vehicle is concerned, the input is a vertical input and which you can definitely declare to be the disturbance input. So, this is the disturbance input to the system. What is your interest? Your interest is that your body should not vibrate. So, it means let me say that this y2 is the output of interest, the vertical motion of the automobile. Let me consider this mass m2 and this y1 as I consider another variable in this system. This is the variable, the y1 displacement of the mass, the vertical direction of course. Now, you see that the input variable is Fw, which is the disturbance in the system, and output variable is y2, the attribute of interest to us, and y1 and y2 and their derivatives, as you will see, will turn out to be the state variables of the system. Let us look at the way we will write the differential equation model for this system. You will recall my statement that we will apply the physical laws to a system, obtain the differential equations, and therefrom we can get a state variable model or transfer function model as the need be. So, in this particular case I will obtain the differential equations considering the electrical analog. One point I like to mention before I take the analog of this particular system is that in this particular system I may not take the gravitational force explicitly, and that is possible only if you consider your reference point properly. Let me say that in this particular case the zero reference for position corresponds to the level surface, but with gravitation acting on the system. So, in that particular case, under that equilibrium position or zero reference position, you will note your springs and dampers are not in the relaxed position, they are getting the gravitational force on them. However, the corresponding position is declared as the zero position of the automobile and the wheels. So, with respect to this position, naturally the model does not take care of the explicitly does not use explicitly the gravitational effect, because it has been accounted for in our definition of zero reference. Yes, please.
Is it the initial rest position?
Yes, initial rest position. At the level surface, when the disturbance is 0, the initial rest position is the zero reference position, and if I measure my variations with respect to that position, the gravitation need not be taken into account. Okay. Look at this particular case now. I will like to write the electrical model for this. Well, there are two nodes. Let me say that the two nodes for me are the velocity v1 of the mass m1 and velocity v2 of the mass m2. Okay? Between these two velocities there are two elements, the spring and the damper. Between these two velocities, spring and the damper, and the values are k1 and b. Okay? Now, between V2 and the ground reference, between V2 and the ground reference you have, let me say, the mass m1. Well, I think looking at this, if you do not mind, that if there is no confusion, looking at this is mass m1. Let me declare this to be y1 and this as y2. There will be compatibility. There is no absolutely no problem. There will be compatibility here. Now, between V1 and the ground, you can say that there is a mass m1, and let me represent it this way as a two terminal element where one terminal is fixed, that is the velocity is measured with respect to this terminal, which is the reference terminal. Between V2 and ground there will be the spring K2 and the mass m2. And how about the force corresponding to the current? This is your force, let me call it Fw. Please see, I give you the diagram again. Look at this diagram. M1 is a node and M2 is another node. These are the two variables of the node. Electrical voltages are analogous to velocities. So, I am considering the two velocities as these two node variables. Between these two nodes I have got these two quantities. Between this node and the ground I have K2 and mass M2. Of course, M1 is with respect to ground and the node V1. So, that is why I get this as the equivalent network, and let me call this as a mechanical network. And if you appreciate this change, in that particular case equations can directly be written in terms of mechanical network rather than converting them into resistance, capacitance, inductance and current elements. We can directly write the equations. Instead of the current balance, now you will have the force balance, current being analogous to force. In that particular case, help me write the equation at node 1. I will write the equation and just you compare whether it tallies with your equation. At node 1, the equation is this: the current through mass m1 or the force m1 dv1 by dt plus k1 v1 it will be b v1 minus v2 plus k1 y1 minus y2 equal to 0. I hope you are getting it. The way you write your nodal equations, I have written the force balance equation, keeping in mind that force is analogous to current. Okay. Look at the second equation now. The second equation will be, well, m2 dv2 by dt plus b v2 minus v1 plus k1 y2 minus y1, what else, equal to Fw. This becomes, did I miss anything? Yes, I have missed, and the thing I have missed is another force here plus K2 y2 equal to Fw. y2 is the displacement of the mass m2. So, this becomes the second equation, which is the equation at node 2, the force balance equation, keeping that the force is analogous to current. I have taken the currents entering into the node is equal to currents leaving the node. This is what I have done. I hope this is okay. Equivalently, you can write the free body diagrams corresponding to the two masses, and from the free body diagrams you can definitely write these force balance equations. They will definitely tally. If there is any question on this, I would like to welcome that at this stage. I hope this is okay. Fine.
What is the reason for the representation of M1 and M2 as you have done?
Reason, please repeat your question, please, little loudly.
So, what is the reason for the representation of M1 and M2 as used by you?
Yes, I have taken M1 as a two terminal element. this is the free terminal. It means this is the node which is the motional variable, and the motion of the mass, that is, this is with respect to certain reference which is fixed. So, if you consider this, the velocity of the mass m1 is with respect to the ground terminal, that is the fixed reference. Similarly, the velocity of the mass m2 is with respect to the fixed reference, and therefore, m1 and m2, though in this diagram is not clearly shown to be a two terminal component, can easily be taken as a two terminal component, one being the ground terminal or any reference terminal with respect to which the two velocities are measured. That is why it is in my diagram taken as a two terminal component. I hope this is okay. Fine. If the first step is over, that is, I have written the two differential equations, equation 1 and equation 2. Now, this constitutes the complete dynamical model of the system. The only thing is that this model may not be convenient for use. I may be looking for a state variable model. If that is the case, help me, what are the state variables you propose? In this particular case, two masses are there, and recall the statement, normally the displacements and velocities associated with the masses constitutes an independent set of state variables for a spring mass damper system. If that is the case, then x1 equal to y1, x2 equal to y2, x3 equal to y1 dot equal to v1, and x4 equal to y2 dot equal to v2 constitutes a set of state variables for the system. Okay. Interest, the output variable y, of course, in this particular case is x1 itself, because I am interested in the motion y1 of the automobile as an important attribute of the system. So, that becomes the output variable. Now, you see that it is just rearrangement of the two differential equations we have obtained in terms of this, that is, I should write dx1 by dt equal to one equation. The other equation will turn out to be dx2 by dt equal to this, dx3 by dt equal to this, dx4 by dt equal to this. These are the four equations, and you can easily manipulate the given set of the given equations, that is the two differential equations, to obtain these four equations. And then these four equations can suitably be put in the standard format of x dot equal to ax plus bu br, y is equal to cx plus dr, where r, as you note, is nothing but your fw, the input to the system, which is the disturbance input. Well, I have rearranged these equations, I project it here and I leave it to you for verifications. These are the A, B and C, A, B, C and D matrices I get just by rearrangement with x1, x2, x3 and x4 defined the way we have done, that is the two displacements and the two velocities. This is the state variable model I get, a 4 into 4 model for a fourth order system. You will have clearly note that the C in this particular case turns out to be only one element, because we had seen your y is equal to x1 itself, which will naturally give you this value of C. Okay? So, this can easily be verified, and I hope I can leave this as a simple exercise for you. Now, look at the transfer function model. If I am interested in a transfer function model, what should I do? I should eliminate the variables in which I am not interested. I am interested in y1, the output of the system, and fw, the input to the system. So, naturally y2, the displacement of the mass, displacement of the wheels should be eliminated. So, write the two equations in Laplace domain, so that elimination becomes an algebraic manipulation. You see that if I write the two equations in the Laplace domain, the equations will turn out to be this way. I can take the same slide here. Just see, this equation in Laplace domain will be s m1, rather s squared m1 y1 s. I hope you are getting it. Directly in terms of y1 I have written s squared m1 y1 s plus it is now b. I write here as s y1 s minus s y2 s plus k1 y1 s minus y2 s equal to 0. This is one equation in Laplace domain which I get. Look at the second equation. Similarly, I will get s squared m2 y2 s plus s b y2 s minus y1 s plus k1 y1 s sorry y2 s.
Could you please go a little slow? We can't catch on with what you
Okay, fine, I will do it, plus k2 y2 s equal to f w s. I repeat, look at this equation, y1 is the velocity. So, it means v1 is the velocity. So, it means v1 is equal to y1 dot or dy v1 by dt equal to y1 double dot. So, this is m1 y1 double dot, hence I have written s squared m1 y1 s. I hope this is okay, plus what is v1? v1 is y1 dot and therefore b s y1 s minus s y2 s, and this is simple, plus k1 into these variables in Laplace domain. I hope this is okay now. Similarly, look at this equation, this component is y2 double dot, gives me s squared m2 y2 s plus s I have taken out s b y2 s minus y1 s plus this is directly coming, there is no derivative involved, this term corresponds to this and this is the Laplace transform of the disturbance variable. So, now you will see in this particular case there are three variables y1 s, y2 s and fws. You are interested in y1 s and fws. So, you have two equations, you eliminate y2 s and this gives you the differential, the transfer function model which I have written for you and I leave it for you to verify. This is the transfer function model which is equal to y1 s divided by fws. It is a fourth order system as you see. The state variable model we had seen. From the state variable model I observed that it is a fourth order system. So, the transfer function model should give me a fourth order characteristic equation. So, I find that the characteristic equation in this particular case turns out to be a fourth order characteristic equation. Even if you have not noted any specific expression, I think you can derive these expressions, you have to concentrate only on the basics. That is, this example I have taken only to bring home this point, that given any physical situation, I will apply the basic physical laws. In the mechanical system, I may use the free body diagrams or I may use an equivalent mechanical network. I get the differential equation model and then transform that model into appropriate form. The two forms useful to me are the state variable model and the transfer function model. This is what I wanted to convey. Okay? Okay, next example. As you said, let me take a little slowly so that you can appreciate and you can check my calculations. The next example I take is that of a rotational system. We will run quite parallel to it. A rotational system, I take this as the load, J2 is the inertia of the load. Okay? This is driven by a motor. And let me say the rotor of the motor and other rotating parts have got inertia J1. I am making the system a little complex compared to the system we have handled earlier. Now, I consider that it is a high power servo, and in under this condition that system is a high power servo and this shaft is a long shaft, the flexibility of the shaft, the torsional effect of the shaft cannot be neglected. So, I assume that the shaft can be twisted and K is the corresponding constant which models this behavior of the shaft. Okay? Earlier I had mentioned that normally servo systems will have two parameters J and B, but such situations also we do come across where the third parameter K is also important. Let me assume that the frictional effect in the system is modeled by this damper, and this damper has got this B as the frictional coefficient, viscous frictional coefficient. So, in this case now I take the input here as the applied torque by the motor, okay? And therefore, this gives rise to the motor rotor. The motion of the motor rotor is given by theta 1 or omega 1, theta 1 being the angular displacement and omega 1 is the angular velocity. The two things at the load end let me take as theta 2 and omega 2. Now, you help me please, and all your queries regarding whether I can take these moment of inertia or mass as a two terminal component or not should be clear. Make an attempt yourself and compare with my result. These are the two basic nodes corresponding to moment of inertia J1 and moment of inertia J2. Okay? So, let me make these diagram. These are the two basic nodes, and let me associate the corresponding variables, the node variables, as omega 1 and omega 2, analogous to two voltages. Now, between these two nodes you see that there is a damper and a spring. So, let me put a spring over here and a damper K and B. This is between these two nodes. Now, let us see what is happening at node W1, that is this particular node. You see that the moment of inertia J1, you take the datum node as the inertial reference with respect to which the displacement or the velocity of J1 is measured. If you consider this, in that particular case, this could be taken as a two terminal component, and let me use the same symbol as I used for mass, there is no problem there as far as symbolic representation is concerned. So, J1 is this terminal now. Look at the torque T. So, naturally in this particular case torque is analogous to current. So, this torque becomes the force variable, or the torque becomes analogous to current variable in an electrical network. Go to the other side, J2 is the second terminal corresponding to omega 2, the angular velocity. So, obviously your mechanical network becomes complete if I write J2 here. This is your mechanical network. Okay? I am giving these networks because I presume that we will be more comfortable with this type of network as far as writing of differential equations are concerned. Otherwise, you please write the free body diagram for J1, the free body diagram for J2, take the force balance equations, you get the corresponding equation differential equation model. So, in this particular case, the two equations turn out to be, just look at this, J1 theta 1 double dot. Now, I am directly writing in terms of theta 1, so that when I transform it to transfer function model I am more comfortable. J1 theta 1 double dot, yes, what next please, plus B theta 1 dot minus theta 2 dot plus K theta 1 minus theta 2 equal to T. Fine. In Laplace domain, right here let me write the equation s squared J1 theta 1 s plus s b theta 1 s minus theta 2 s plus k theta 1 s minus theta 2 s equal to T s. Okay? Now, let me get the second equation. The second equation is J2 theta 2 double dot plus B theta 2 dot minus theta 1 dot plus K theta 2 minus theta 1 equal to 0, and the corresponding Laplace domain equation will turn out to be s squared j2 theta 2s plus sb theta 2s minus theta 1s plus k theta 2s minus theta 1s equal to 0. I hope the speed is all right now. This is the situation which is identical to the earlier situation. So, in the earlier case, if there was any confusion, please you can bridge the gap by looking at this example. There are 3 variables now, the input variable t and the 2 variables are theta 1 and theta 2. If I am interested in theta 2, the moment the displacement of the load, so naturally theta 1 variable has to be eliminated, and I hope this I can leave as an exercise for you. You can just look at the result, elimination of the variable theta 1 and rearrangement in the standard form of quadratic lag. You will recall this is a standard quadratic lag, this particular term, a second order term, is a standard quadratic lag. So, rearranging the equation in the quadratic lag gives me this result. So, do not worry, even if you do not note it, you just keep this in mind that Gs equal to theta 2s over Ts should be rearranged in a form where the time constants and quadratic lags do appear, because these are the terms which represent the personality of various factors in a transfer function model, as we have seen earlier. Okay. I think with this I will like to conclude that the modeling of mechanical systems is over. I will take more examples in the tutorial classes only. Okay. Let me go to another phase of modeling. As far as the overall system is concerned, we know that here is a plant. The so called mechanical systems means which we have considered means actually we have considered the models of the plant. Various plants we have considered, more of them will appear later. Now, if this is the situation, after that I have an actuator. For a typical mechanical system, say motor is an actuator, because it will drive your load, which is the plant. And after this, you see, if motor is an actuator, so you are controlling the power to this particular actuator, so that your output follows the command. So, it means here is what I call as a controller. Okay. The controller should get information, this is what we have done already, should get information about the command signal, and it should also get information about the actual controlled variable. On the basis of this information, it controls the power supply to the actuator. The actual information about the controlled variable will normally come through a suitable sensor. Okay. I need your specific attention here, because the role of electrical engineer I am going to define as far as total control system is concerned. You see that we have seen our plant to be of mechanical nature. The other plants which we will come across will be mostly from the thermal field or for the control of liquid level and other variables in which we normally encounter in industry. So, where is the electrical engineer's role as far as these systems are concerned? You will please note that a sensor, I have already said this point, told this point to you, a sensor normally gives rise to high frequency noise, okay, and therefore, to filter this noise you require suitable filters, otherwise the noise will also go in the loop and the performance of the control system, of the feedback control system will be deteriorated. Okay. One point, you require noise filters that you will design as an electrical engineer. The sensor's output normally will be in millivolt, milliampere. You require amplification of that to make it compatible with the standard input signal or to make it usable by the controller hardware. So, it means suitable amplification or suitable conditioning of the sensor output will be required, and that also you will do. Lastly, and the most important, the controller over here, which is the brain, all these muscles are being controlled by this brain, and the brain is electrical in nature. This controller, as far as the today's trend is concerned, is either an op-amp circuit or a digital computer. Well, in the process industry particularly, pneumatic controllers, hydraulic controllers were used earlier, but these either have been replaced or are being replaced gradually. The trend is towards op-amp circuits and digital computers, giving you in this particular case the brain of the total control system. Well, I do not think I need take any examples of filters or amplifiers or op-amp circuits, because these are very well known to you. I simply wanted to bring home this point that the electrical circuit will be embedded in the total control configuration at appropriate locations, and they are crucial part of the total control system, the controller being the most important part, which is the brain of the system. So, let me just quickly glance at the type of op-amp circuit which will sit in this particular block, the controller. It is only a quick glance and not the details of the circuits will come. Look at this basic op-amp circuit. What is this circuit doing? Look at this please. I can write the transfer function of this circuit immediately. E naught S over E I S equal to, please help me, minus R2 by R1. So, it is acting as an amplifier, and I require amplifier or a proportional controller in my control configuration. Okay. Now, the minus sign, I may like to get rid of the minus sign. Well, put an inverting amplifier in series, in cascade. Let me say R, and now if I take this as E naught. So, E naught S in that particular case, E naught S over E I S becomes equal to R2 by R1. It is an amplifier, and the gain of the amplifier can suitably be controlled by selection of appropriate resistor values. Okay. This, as I mentioned, well, I will be using the proportional type of control logic or proportional control, and wherever such a situation comes, this type of circuit will be utilized there. Well, take up another circuit, a simple circuit again, and let us say what is the behavior of this particular circuit. I have now a resistor and capacitor in parallel, in series over here. So, let us write this model for this particular circuit, E naught S over E I S equal to this impedance divided by this impedance. What is this impedance? This is, as you see, R2 plus 1 over SC divided by R1. This becomes the gain of the transfer function of this particular circuit. Now, help me please, what is this equation? This equation, as you see, is equal to minus R2 by R1 minus 1 over R1C 1 over S. I will like to look at this equation in a different way. For me, as far as the control system is concerned, it is a PI controller. Let us see how. Can I write this equation as E naught T equal to minus R2 by R1 EIT minus 1 by R1C E tau d tau. It is a PI circuit for me, and you will see that in the controller block many a times PI circuits will be used. Rather, if you do not mind, I can make a statement here, almost 75% of the industries in the process field use PI controllers. So, it means naturally this type of configuration is going to be important as far as the process control applications are concerned.
What's the PI controller?
PI controller, as you see, though the details are yet to come, I will like to take the complete block, or let me redraw it, does not matter. This is your command circuit, command signal. Let me call this as R, reference signal or command signal. This is an error detector, plus minus here. Let me say this is an error detector and the error is E. Rather E cap we have used the actuating error. Here is a controller, and let me say it is the plant. I am merging the actuator also into the controlled system and calling it a plant to get a simplified situation, and here is a sensor. Now, you see that this controller has got information about the error between the command signal and the actual signal, and this brain or this particular block is going to control the power being supplied to the actuator of the plant. Now, you will find that there are different ways this brain will act. One of the ways is this, that it controls the power proportional to the error signal. I call it a proportional controller, and the first op-amp circuit could be used over here in this particular situation. The other situation is, which is commonly used in industry, that this controller generates a signal which is proportional to the error as well as proportional to the integral of the error. So, it means the signal at this particular point is a sum of two components, one component being proportional to the error itself and the other component being proportional to the integral of the error. So, the concept as to why do I need it, I think we can leave it for this discussion later. But at this juncture you can see that such a situation may be required or will be required by a controller, where a signal which is a proportional signal to the error and a signal which is proportional to the integral of that particular error is required, and hence a PI circuit will be in use, and the term PI controller I am referring to corresponding to this situation. Similarly, since the block diagram is in front of me, I can refer to other situations as well. If the signal at this particular point is proportional, that is, let me call it U. U is equal to EKC E cap T plus KD d E cap T by dt, which is the derivative of the error. The corresponding controller is a PD controller, proportional derivative controller. In general, a controller block may consist of a circuit which generates all the three components, the proportional component, the derivative component and the integral component, and suitably adds up these components to generate a signal which then in turn is going to control the power supplied to the actuator, power to be generated by the actuator. So, in that particular case that will become a PID controller, and PID controller is a term which will be very frequently coming in our discussion. The logic behind its use I will like to postpone for a later discussion. Quick look at this particular circuit. Just look at this circuit now. The impedance here is a parallel combination of R1 and C, and this impedance here is a pure resistor. Therefore, E naught S over E I S turns out to be equal to, please help me, 1 over, in this particular case it is R1 into 1 by SC, sorry. So, first let me take this as R2 divided by this impedance R1 into 1 by SC divided by R1 plus 1 by SC. I want you to manipulate and get convinced that it is a PD circuit, proportional derivative circuit. Just the manipulation of this equation will give you proportional derivative circuit, where the two constants will turn out to be in terms of the circuit parameters, which are R1, R2 and C. Okay? I hope this manipulation will be easily done by you. So, let me look at this particular circuit. This circuit is a PID circuit. Again, in this case manipulation I like to leave it to you. The impedance Z1 here, the impedance Z2 here, let me say E naught S over E I S equal to minus Z2S over Z1S, Z2 here and Z1 here. Now, well, again a little exercise for you, get the values of Z1 and Z2, get the transfer function model, and from this particular model you will see by manipulation that E naught by E transfer function is the transfer function of a PID circuit, that is the output here is an appropriate combination of a component proportional to AEI, the proportional to the derivative signal of EI and the integral signal of EI. This I leave it to you, please. I hope this is okay. So, this is the electrical component in the overall control system, the electrical components being coming in terms of the signal conditioning at various places, the controller circuits, op-amp circuits, digital computer circuits we have not taken, and I do not think we will be able to accommodate the digital computer discussion in this course. We will primarily concentrate on analog controllers, and therefore, op-amp circuits will come in our discussion. And it does not mean that digital control circuits are not important, they are rather more important, they are gaining importance. However, we have left this discussion to the second course on control engineering. Okay? And the third component I said is the filter in the total system diagram. After this, the electrical component is over. Now, let me say that what are the equations from the thermal systems we will be requiring in our discussion. Two more physical systems please, thermal systems and liquid level systems, and after that I think we are ready to take on to the overall control system models, and therefore, one more lecture only on the dynamic models and dynamic response will be there. Thermal systems, maybe a system example may come next time looking at the available time, but the basic equations can be given right away, so that you can revise those equations before coming for the next lecture. The basic equations are the following. Let me consider a wall of any material with surface area A, please see a revision for you, surface area A and the thickness let me take L. Okay. Maybe this type of diagram. Theta 1 is the temperature on this side, theta 2 is the temperature on the other surface. In that particular case, the heat transfer through this wall is given by H equal to sigma A theta 1 minus theta 2 divided by L. Okay. This is the heat transfer equation, but again please note, all the time I will not be worried about the basic parameters of the thermal system. I will just see that well an analogous electrical system will help me very much in visualizing the dynamic behavior of this particular system. Look at the units, H is in joules per second, A in meter squared, here I have meters, and theta in degree centigrades, and the units of thermal conductivity of the material then can appropriately come from this equation, sigma the thermal conductivity of the material. Okay. But you see that this heat transfer equation for me becomes equal to, is given by H equal to theta 1 minus theta 2 divided by R, where R is equal to sigma A by L, L by sigma A. R is equal to L by sigma A. Please see that this R is the conduction resistance, the conductive resistance of the material, and wherever I need this heat transfer equation, I will be using this parameter rather than going to the basic parameters of the system. H, the heat transfer, joules per second, the heat flow in joules per second is equal to theta 1 minus theta 2. the temperatures in degree centigrade divided by R, where the units of R can easily follow from the basic units given over here. So, this is one basic equation which I will be using in my discussion. Now, the other way the heat transfer takes place is at the liquid solid interface. At the liquid solid interface, my heat transfer equation will turn out to be of this nature: H equal to U A into theta 1 minus theta 2. Again, please see, I will view this equation as theta 1 minus theta 2 divided by R. Look at the basic parameters of the system. U is the film coefficient at the solid liquid interface. A is the surface area of contact, and I am now taking R equal to 1 by U A is the convective heat transfer resistance. So, for me the basic equation now becomes H equal to theta 1 minus theta 2 divided by R whenever the convective process is going on. You will see that the parameters of interest to me will be the resistance parameter as far as this dynamical behavior of the thermal system is concerned. The capacitive parameter comes from the heat storage. Look at the heat storage, the same wall example which I had taken. The heat storage will be given by MC. You see that H equal to MC d theta by dt is the basic equation. You can see this is heat flow rate in joules per second, mass is the m is the mass of the material whose heat storage capacity is being considered, C is the specific heat of the material. I am not writing here, hoping that you already know it and you can quickly write, and d theta by dt is the rate of change of temperature. So, the basic equation, the heat storage equation becomes H equal to MC d theta by dt, where theta is the temperature of the material under consideration. In that particular case, this can be written as C d theta by dt, where C equal to MC is the thermal capacitance of the material. So, for me now, as far as a solid material is concerned, if well, this I can believe that the thermal systems have not been done, but anyhow I can repeat this, there is no problem. How about the first equation please, the conduction and the convection processes, is it okay or does it need any repetition? Convection, okay. If you see that the convection heat transfer should be explained. You see, consider a fluid solid interface. Let us say that the heat transfer is taking place at the fluid solid interface and the area of the contact is A, and U is a parameter which is the film coefficient and which regulates the heat transfer. The U parameter is the film coefficient. So, the basic thermal equation is this, that the H the heat flow rate is equal to, as I have given over here, as I have given earlier, UA into theta 1, the temperature of the solid, minus theta 2, temperature of the liquid, if the heat is flowing from the solid to the liquid. The reverse will occur if the heat is flowing from the liquid to the solid. Let us assume that theta 1 is the temperature of the solid, which is at higher temperature, theta 2 is the temperature of the liquid, which is at a lower temperature. So, theta 1 minus theta 2 is the net gradient across the film, okay, and this gradient, the theta 1 minus theta 2 into UA, U is the film coefficient, becomes your heat transfer rate. Now, what I have done is that I have recognized this equation considering H identical to current. Please see, I equal to E by R is my basic equation in an electrical circuit. So, considering H analogous to current, temperatures analogous to voltage, I recognize a resistance parameter, and this I have written as theta 1 minus theta 2, the temperature difference, as the potential difference. Temperature difference across the film is equivalent to potential difference divided by R, which is the resistance offered by the convective process, and the two parameters are the film coefficient and the area of cross section. I hope this is okay. Fine. Similarly, if you want me to repeat, I will take this material again. Okay. Let me say m is the mass of this material, and let me say that theta is the temperature. Of course, one thing is obvious, you see, I am not repeating all those things. The system is actually a distributed parameter system. It is a distributed parameter system, but you are approximating it by a lumped parameter system. That is why the total mass is being approximated to be modeled at a point mass of temperature at temperature theta. So, this is a point mass at temperature theta. Okay. The total heat storage in this particular case is mc, and the basic equation which I have written is this H, and the consistency in the units can be taken. C is the specific heat of the system. You will find that mc represents the heat storage, and the rate of rate of heat storage is given by mc d theta by dt. mc theta is the heat storage. You will find that, please see, mc temperature theta is the heat storage. So, I am considering it as rate of change of heat storage, because this is H, joules per second. Since it is joules per second, I am taking here as, to make it compatible, mc d theta by dt, and corresponding to the equation I equal to c dE by dt, my equation becomes, this is equal to c d theta by dt, where c is the thermal capacitance. Okay. Since it is analogous to this particular circuit equation, I is equal to c dE by dt. Consider, just a couple of minutes are available with me, and therefore, I can write the tank also. This is your tank. This tank has got volume V. Please give me the equation now. If you got my point, you can give the equation to me. What is the thermal capacitance of the liquid in the tank? If I get it from you, it will be, it will confirm that you have understood my point. I want from you the thermal capacitance of the liquid in the tank. Okay. V is the volume in meter cube, rho is the density kilogram per meter cube, and C is the specific heat. Rho Vc becomes, obviously in this particular case, please see your equation H is equal to V rho C d theta by dt, where theta is the temperature of the liquid in the tank, which again I am considering to be a single temperature, that is lumped parameter approximation is there. So, in this particular case, this can be modeled as C d theta by dt, where C is the thermal capacitance of the liquid in the tank. With these two, and you will please note, in thermal systems there is no parameter identical to inductance or equivalent to inductance. So, we will have resistance capacitance circuits only whenever I write dynamical equations for a thermal system, and the example of the thermal system I will take in the next class. Thank you.